Okay, thanks for coming. It's my pleasure to introduce Ms. Sahinidis, who is the John Swellingen Professor and Director of the Center for Advanced Force Decision Making at Carnegie Mellon University. He joined Carnegie Mellon in 2007 after a 16-year career in the University of Illinois at Urbana, where he taught in industrial engineering and chemical engineering. Some of us know Nick because of Baron. Baron is, I think, the first global optimization solver for problem optimization of MINLPs. After that, he has done work on surrogate modeling, which is going to be the focus of his talk today, and specifically within the interest of the Institute for Machine Learning and Algorithms for Model Building. I think this is a very, very good match and a very interesting talking to all of us. Nick has been recognized by the Informed Computing Society Prize in 2004, the Deal Hayes Prize from the Mathematical Programming Society in 2006, the Computing in Chemical Engineering Award in 2010, the Konstantin Karateodori Prize in 2015, and the National Award and Gold Medal from the Hellenic Operational Research Society in 2016. Has been an Informed Fellow since 2014, and with that, I'll let Nick go through his
All right.
talk on ALAMO.
Thank you, George, very much for the introduction and the invitation. And thank you all for coming here. It's a great day out there, so I'm impressed so many people came here for the seminar. So I want to talk today about methodology for doing machine learning, and of course that's a very popular topic nowadays. I'll try to relate what it is that we do to work that's out there, and also the kinds of applications, systems type of applications that have motivated this work. Let me first acknowledge Alison Kozat. Alison was the first PhD student that worked on this project. David Miller is our collaborator from the Department of Energy. He's motivated quite a bit of this work, actually, and contributed to it. And Zach Wilson is a current PhD student working on the project. So I'm going to be talking about a problem that's fundamental in computing nowadays, very popular in particular. I have a system that has inputs that I've denoted here by X and outputs that I've denoted here by Z. I'm allowed to vary the inputs and measure the outputs. And what I'd like to be able to do is use the data that I take to figure out the input-output relationship. So this function here that I'm showing as Z equals f of X is what I would like to learn from measurements. So as I said, it's a classical problem in machine learning. Where I come from in chemical engineering, typically these black box systems could be systems that we can actually take measurements from. We have a piece of, we have experimental equipment, we can run and take measurements, or we might have a simulator that we can run to take measurements, okay? And the examples I've listed here pertain to applications in chemical process systems, but the problem I'm looking at is a generic one. I have an input-output system, I have measurements, I might be able to collect additional measurements, and I'd like to build a model, okay?
Not dynamics.
Not necessarily. We can deal with dynamics as well, but I'm not going to talk about dynamics today. I'll talk about static stuff. You could think, though, as one of your inputs, time being one of your inputs in this context, and model the system as a function of time as well. So, as I said, machine learning nowadays is very popular. There are many algorithms out there. Google is using deep learning. Microsoft is using deep learning. IBM is using deep learning. The question is, what do we want to do in this area, and why do we care about developing a new modeling system? Okay. So very quickly, where we came from, and then why we are looking into developing new methodologies. So someone from the Department of Energy basically came to us and said, I have a simulator, very detailed simulator that can model this very complex process. Each of these pieces of equipment is very complex. We have differential equations describing it in space, in time, whatever. And we have the detailed model in place. We would like to be able now to optimize this complex system with all the interactions. And eventually, we would also like to be able to design systems of this sort. So we would like to figure out whether to place this piece of equipment in there or not, whether to have certain recycle streams or not. I would like to do all that based on basically, these simulations. And of course, that's the problem that we started looking at. And very quickly, you realize that looking at this problem on top of a simulator is a very difficult problem to address. Why? Because, well, if the system is a black box, I don't quite have algebraic information for functions. It's very difficult to get gradients. I can get them numerically, but it's going to be expensive in some cases. And if there are local minima, it's going to be very, very hard to actually optimize and find the best solutions. In fact, if there are discrete decisions, these performance curves are going to be shifting all over the place. It's going to be very, very difficult to find global optima. Another issue here is, of course, that the simulations might be costly. In our case, we're using, something like Aspen might take a few minutes, but if you're looking at optimizing on top of finite element simulations, those simulations might take hours, weeks, even longer. You don't want to be drawing too much data, okay? So this is not going to be a big data problem in some sense. Even though I can potentially draw as much data as I want from the simulator, I don't want to do it. I want to avoid that if possible because it's expensive in some cases. And last but not least, simulators are not really robust in the sense, you spend a week trying to get something like Aspen to converge, and then you change one parameter, you change the recycle stream, and you realize this thing is not converging anymore. Why? Because there's nonlinearity, so much of it underneath in the equations that it's very hard to get them to converge. So that's the setting that we were looking at, and then we said, okay, let's do the following. Let's take this system that we are interested in optimizing, and let's break it down in pieces. So I'll take the system, and I will break it down in the blue part, the green part, and the red part. And now what I'm going to do, I'm going to simulate each part independently. I'm going to either simulate or take measurements independently. And what I would like to do in this context is actually build surrogate models for each of these pieces of the large system. What's the idea? Well, the idea is the simulator may not converge that easily for the overall system, but it's much easier to get it to converge when applied to a small piece of equipment. At least chances are higher that you'll be able to converge there. So we will do the simulation of independent pieces, and we will extract algebraic surrogate models for each of these pieces. Then we will lump all those models together into a single algebraic formulation that I would like to optimize so as to optimize my system. Now, of course, there might be some simple mass balances here and some other basic understanding of the system that I have available in algebraic form, in which case I don't need to simulate. I would just put all that into this formulation here before I optimize. Now, one of our challenges is right here. If I use something like a neural network to model one of these pieces, it's going to be very difficult to optimize on top of that neural network. The functions are very rugged. It's going to be very difficult to find global optima, and if I have discrete decisions at the same time, such as do I use this piece of equipment or not, the problem is going to be very difficult to solve to optimality. So for that reason...
You handle a lot of feedback and things like that. You do the individual blocks.
Very simply, basically, you would say you had an algebraic relationship output from one stream equals to output from a process system, from a piece of equipment equal to another one. So now at this point, what occurred to us is, of course, it would be nice if the system, if the models for these pieces were as simple as possible. Okay. So what would that buy us? Basically, it would make this optimization formulation much easier and more amenable to the technology that's out there for algebraic optimization. And I'll come back to this point towards the end of my talk and explain how all this thing could work. So here are some of the attributes that we would like our models, our surrogate models to have. Of course, we want them accurate. Everybody wants that in machine learning. But I also want them simple as possible. And as I said, the primary motivation is that my models will be more amenable to global optimization down the road, and I'll be able to find global optima. Another advantage of having simple models is that actually you can look at them and interpret them physically. that's a bonus. It's not a requirement in my context. Another constraint is that I would like to minimize the number of samples, the number of measurements that I take, because in many cases these are very expensive. Okay? And last but not least, I'd like to have the ability to impose physics and chemistry whenever possible on the response surfaces that I generate for my surrogate models. Okay? And again, this is something that's different to what is out there in the literature, and I will talk more about this step as we move forward. All right, so I'm going to stay at the very high level, just describe the overall approach, and I'll try to use examples as much as I can. So here I have a black box function. I don't have it available in algebraic form. All I can do is I can query a simulator, or I can run an experiment and get function values. So we will start by sampling the system, and let's say in this case you sample these blue dots. And this problem, of course, is now related to design of experiments. And there are many techniques one can use in this context. Latin hypercube sampling, D-optimal, A-optimal, and all sorts of different design techniques, design of experiment techniques. And let's say we start with these measurements. Okay? We will build a model, and I will explain in a bit how we do this, how we go about building simple models. And as you can see, this blue model...
Do you know how to select how many number of points you need for a system, or just doesn't matter?
It's not essential, but it does help produce an optimal design. You've seen that. It's not essential, but it helps. So in this case, as you can see now, I have a model, a blue model that is perfect fit as far as the measurements are concerned. But on the other hand, it does a pretty bad job in part of the domain where I haven't sampled. So the next step in the algorithm is to do what we refer to as adaptive sampling, to identify points in the domain where my function, my current surrogate, breaks down. We don't necessarily look for the worst violation, just any point where the function is not doing well will do. We will take that point, we will add it to the training set, and then we will repeat the process of building the model and until eventually we have some statistical evidence that we have sampled enough, and therefore we don't need more data points, and we will terminate at that. Okay, so let's talk a little bit about now the various steps of the algorithm. First of all, how do we go about building models? I alluded already to the fact that we're looking for simple models. There are many techniques out there, things such as neural networks, kriging, radial basis functions. They can be used to model just about anything, arbitrarily, closely. The only thing, as I said earlier, is that these are complex models. You can go at another extreme and use linear regression, and unfortunately, this is not going to work if your system is sufficiently nonlinear. So we're going to try to stay somewhere in between and try to get as simple models as we can while the models are still accurate. Okay? All right, so here's how we go about this. We will postulate a number of basis functions, things such as powers of the input variables, products of powers of the input variables, things such as exponential, logarithmic functions, and a few other things. Now, as you can see here, I'm also including radial basis functions, which might seem contrary to what I've been preaching, but the only reason we have it there in the software is so that we can ask the question every now and then, well, would adding a more complex basis function give me something in this particular context or not? Okay? And of course, we do allow users to specify their own basis functions, and that's very important in certain applications. For instance, if you model a heat exchanger, you need something called log mean temperature difference to make sense out of the system. All right, so having now these basis functions, you might end up with a very large number of these. So potentially we start with a very large number because we don't know a priori going in how many functions we are going to need. And what we are going to do now is we are going to pose a very simple regression problem, linear regression problem, that it's now linear in terms of those nonlinear basis functions. So these betas are the regression coefficients. And my basis functions for this example are linear in terms of the input variables, x1 and x2. I also have an interaction term and some exponentials. And of course, the challenge here is if you put too many of these functions in there with a relatively small data set, you're going to be overfitting, and you need to somehow avoid that. So you need to somehow extract a subset of these basis functions that makes the most sense. So what we are going to do here, we're going to use some information criteria from the statistics literature to achieve this goal. And in particular, well, I should point out that there's many techniques out there for dealing with this problem. There are greedy heuristics out there in the literature that basically say, let's go through these basis functions one at a time and do some sensitivity to decide whether to keep them in the model or not. There's something called the lasso technique, of course, that does provide sparse models by minimizing the L1 norm of errors. And the idea there, the L1 norm of these coefficients, the regression coefficients, and the idea there is by minimizing that norm, you hope that a smaller number of those regression coefficients will become non-zero. And then there's something called best subset selection methods. These methods basically introduce a binary variable for each of the potential terms, each of the bases. And its binary variable is supposed to turn on or off the corresponding term in the regression model. Okay? So I'm going to go there. The first question that we asked was basically, even though we know that lasso does give sparse models in comparison to standard regression, we wanted to know if we can actually get even sparser models from this integer programming.
Well, why is lasso more expensive than backward or the forward selection?
Because basically...
it's just solving one problem.
Okay. Well, they solve what they call a complete path.
Okay. So the lambda is the parameter that you
The lambda is a parameter, so they do many more of those. Okay. So as I said, we're going to be going now for using this information criteria. Things such as Sahinidis information criterion, the Bayesian information criterion, and a number of others. And basically, what all these things do here, they have two terms. The first term, and I think it's easier here to look at Mallow's CP. The first term, here I have the difference between my measurements and my linear regression model. This capital X is the nonlinear transformations of lowercase x, my input variables. So here, this is nothing else but the standard least squares kind of problem. But now we have the second term here in terms of this P, and P denotes the number of terms that you have with non-zero values in the final surrogate model. So all these models basically look to balance the fit, this sum of square errors, against the complexity of the model. And complexity here is expressed in terms of P, which of course is in terms of binary variables that turn different basis functions on or off. So at the end, you end up with a formulation that has a mixture of continuous and binary variables, and you have nonlinearities. So what you have is a mixed integer nonlinear optimization problem, which in general is a difficult model. Okay? Now it so happens that there is technology out there, and technology that we've been developing for the last 25 years, something we refer to as branch and reduce, and I'm not going to get into details. All I'm going to say is that there is even software that we've been building for the last 25 years. These algorithms are deterministic. They are not of the stochastic type. They are of the branch and bound type, and as a result, they do guarantee global optimality even when the continuous relaxations of these problems are non-convex and have multiple local minima. In terms of software for this type of problem, actually, at this point there are 5 deterministic branch and bound solvers addressing mixed integer nonlinear programs. Baron appeared about 10, 15 years ago, but then more recently we've seen the appearance of Skip, Antigone, Lindo Global, and Quain, all of which are addressing the same class of optimization problems, mixed integer nonlinear programs. And what I'm showing here is a performance profile comparing these solvers on the so-called mixed integer nonlinear programming library version 2, for which down here I have listed some statistics on the problems. So in particular, I'm listing for the number of constraints, variables, and discrete variables in these problems in this library. We're listing the average number as well as the range. So for instance, we have problems with 1 constraint as well as problems with 164,000 constraints in this data set. The average number of constraints was around 1,900. So these problems are not small. And I should say that up to 5 years ago, we were nowhere close to being able to solve problems of this complexity. But there was a lot of competition between these codes and the research groups behind them that led eventually to this current state of this of the art in this literature. This is the percentage of problems being solved by these algorithms. And as you can see, Baron, for instance, can solve about 60-some% of these problems. The more time you give it, the more problems you are able to solve. By the way, the can solve line basically says what is the percentage of problems you can solve with the entire collection of solvers available to you, which is telling you that Baron is not the best solver for all these problems. That's about, the difference here is about 7%, which means there's some other solvers in there that are doing better than Baron for some of these problems. And the fact is these are empty hard problems, so you take the wrong turn, the branch and Baron tree, you may end up taking too long to get the final solution. But the bottom line is, chances are about 60-some% or 70-some% that you will be able to solve your problem with one of these algorithms.
How did this compare with CPLEX and all this?
Well, CPLEX does not apply to these problems because CPLEX cannot handle arbitrary nonlinearity. But other than that, in the case of mixed linear programming, these solvers would also be applicable, but they would be slower than CPLEX because they don't exploit linearity as much as CPLEX does.
So what problems cannot be solved? You have a 30% problem cannot be solved. What do you mean? How do you define it?
And by the way, what I mean, when I say here solved, I mean we prove global optimality. So the upper and lower bounds that the algorithms provide are exactly equal. For the remainder 30%, these algorithms do provide some solutions. We just don't know whether they are the global solutions or not.
What kind of gaps are you getting? Duality gaps?
The duality gaps vary quite a bit.
Okay.
Yeah, I'll just leave it there. I don't want to talk too much about. All I'm saying is there is the technology that can now solve some problems, at least, that we couldn't solve 5 years ago, and that's the technology I'm going to be investigating in this context, in particular for optimizing, let's say, the Bayesian information criterion. We're working here with some benchmarks from the UC Irvine and CMU datasets, and what we're showing here is, well, first of all, we are comparing different optimality criteria. In terms of CPU time, the Bayesian information criterion does much better than other criteria. Well, the Bayesian is actually one of those that has a convex relaxation. When you drop in the gravity constraints, that's the reason. More interesting in terms of the quality of the models that they provide. Again, the number of spurious variables introduced by the Bayesian information criterion is lower in our experiments, and you don't deviate too much from the true model. Okay? Now again, this is for a specific data set, but we do know that there are different assumptions between the different optimality criteria. So some of them make more sense than others in the context of certain applications, depending on the types of errors that you have in your measurements. So in terms of the implementation, of course, we have implemented all the different criteria and can switch back and forth and see what types of solutions they provide. Okay, so that's how we're going to go about building models. We're going to be utilizing one of these information criteria. Now, the next step I want to talk a little bit about is the adaptive sampling step. So just again to remind you, I have a tentative surrogate model, and I want to sample somehow the domain for points where the model breaks down. We're going to be formulating this as an optimization problem. In particular, I have the true model, this function z, that's unknown, and I have the surrogate model that I have a variable in algebraic form. And I would like to maximize the difference over the domain of the input variables. Right? It's simple to state, but it's a difficult optimization problem because it's a black box problem. This function is not available to me in algebraic form. But I can query the simulator. I can sample anywhere I want. So we are approaching this by using a class of algorithms known as derivative-free. And these algorithms actually include all the genetic algorithms and the particle swarms and simulate annealing and all those algorithms, but they also include variants of branched bound and other interesting algorithms. And what we did in a computational study recently, we actually compared about 25 or 30 different derivative-free optimization solvers. And we found that as long as the dimension of this input space is not too large, so no more than about 10 to 20, many of these codes will actually work very well. SnopFit, which was developed at the University of Vienna by Neumeyer's group, in fact did very, very well for the testing that we did. And we used a collection of about 500 test problems that was quite extensive. And Snowflake was able to actually find global optima for most of those problems in a relatively small number of iterations. So what we're going to be doing, we're going to be using Snowflake to do this adaptive sampling. One of the good things with Snowflake is that it will sample at the same point if needed to get a model for the variance, in essence, model the measurement errors, and things of that sort.
Are there techniques like this for discrete X?
Yes, some of these techniques will work with discrete spaces as well.
Okay. Where I'm selecting maybe one of the
Yes.
index. Okay.
Yeah, they can deal with categorical variables and discrete variables in general.
So is a Z scalar or is it multidimensional?
That's objective function.
So Z can be multidimensional, and in practice what we actually do, we decompose this, we work one variable at a time for efficiency reasons only. But yes, in general, you would be looking at a multidimensional problem, and that's not what we're doing right now.
So could Z be 0?
Be anything, yes.
So then definitely the problem's not.
Oh, you mean in this context? Yeah, sure. Yeah, you would have to scale appropriately. I guess in this case, we did some sort of a normalization. Yes.
I mean, those are the typical.
Yeah, I mean, this is
the
the implementation details. All right. So we're going to be using this kind of algorithm to do sampling. All right. And the last thing I want to talk about from the methodological point of view is this concept of constrained regression that we're going to be introducing now into the field of regression. That says the following. Here, again, by way of an example, let's say that I want to model the concentration of a species over time. I have measurements, the white dots. There are 7 measurements over there, and I'm comparing 2 models, the green model and the black model. If you look at the black model, it does a perfect job in terms of these measurement points. It fits them perfectly. The green model is not as good in a couple of places, but it has a significant advantage. It does not predict negative concentration like the black model does anywhere in the domain. Okay? I would like to have the capability when doing modeling of quantities for which I know they are non-negative. I would like to have the capability of getting models that predict well at points where I don't have necessarily measurements. Okay? So I want to impose constraints on the response surface itself. Okay? You can now go a bit further and say I want to be able to extrapolate in domains where I don't have measurements, and I want to still be able to enforce lower and upper bounds on my response surface. Okay? So I call this constrained regression, but there is something called constrained regression in the literature that's a little different. Okay? And I will illustrate this in this context of, again, in terms of a small example, showing a standard regression problem with 4 measurements, 2 regression coefficients. These are my measurements here, the z's. Z hat is my algebraic surrogate in terms of 2 regression coefficients. There is something called constrained regression in the literature. Take a standard regression problem and add to it linear constraints in terms of the regression coefficients. And this is just an example. This problem here is not much harder than this one. It's polynomially solvable. There's software for it out there. You can solve this problem. The only challenge is I don't know of systematic ways for going from this constraint to imposing a constraint on the response surface itself. Okay? You can do it in special circumstances, but not in general. And the problem we actually want to solve is of the latter type, namely, I want to do constrained regression, I want to do regression, but now I have a constraint that says my response surface, such as my concentration, has got to be non-negative everywhere in the domain of interest. That now makes the problem a semi-infinite optimization problem. I have to enforce that constraint everywhere in the domain. That's the hard part of it. So what we're going to do here, we are going to somehow figure out, start with this intuitive constraint on the response surface, and infer from it non-intuitive constraints, such as these, that I can then use to solve this interesting, this simple regression problem in order to get a solution for the difficult regression problem. Okay? So again, how do I do this? Well, again, by way of an example, let's say this is my regression model, 2 regression coefficients, single input variable, I have a linear and a cubic term in the model. The constraint I want to impose is that my my model predictions must be non-negative everywhere in the domain. And now note, if I go and take this domain and I discretize it, say at arbitrary points, this will become a linear constraint. So let's do this at 4 points. Let's take 4 points in the X space and fix them, and let's not worry about what the points are. But basically, I guess we can see here it's 0.24, 0.281, and so forth. Once we have fixed the points in the domain, now this regression problem becomes, it's the easy regression problem that I can solve with off-the-shelf software. Now the hard thing though is, this is not, satisfying these constraints is not necessarily going to satisfy this constraint for all points in the domain. So what I have to do now, once I have a solution from this regression problem, I have to take the regression model and ask the question if this constraint is satisfied everywhere in the domain. Well, that's not too hard to do, conceptually at least, because the betas are now fixed. They come from the regression problem. I'm looking now for an X that minimizes the left-hand side. So what I have to do here is solve a global optimization problem. And I have to solve it to global optimality in order to give proof that I have solved the semi-infinite optimization problem. But you already know, you can use Baron to solve these global optimization problems. And in fact, this is going to be typically an easy optimization problem. It's in one-dimensional, two-dimensional problems, and you can deal with those rather easily. All right, now here are some of the things you can do with
So if not, what do you do? You add more points?
You add more points. You increment. It's a cut and plane type of algorithm. Yeah. And you increment your collection of sample points. Okay, so here are some of the things that you can do. Non-negativity on the response surface, more general lower and upper bounds on the response surface. These are the things we have already implemented.
I guess you will know what X, where it is deviating from 0, right? So you can just add that point.
Right.
Okay.
Right. Some of the things that you can now begin thinking about is actually imposing constraints on multiple response surfaces, response variables at the same time. So for instance, if you're trying to model mole fractions, and you know those have got to sum up to 1, you can think in terms of algorithms to do this kind of constraint regression on top of these constraint regression problems. You can think of imposing constraints on the gradient of your response surface. You can think of imposing these constraints in extrapolation zones where you don't have measurements. You can think in terms of imposing these constraints on an entire surface, an entire collection of problems, points, and so forth.
So if the constraints not satisfied, so you add those points in, or
Yes.
how many points do you add in general?
Again, it varies, but typically a small number is sufficient.
So just
At
for
least
the
you'll
maximum
know,
point?
you'll know one point where it's not satisfied, right?
Yeah.
Right. And you don't have to solve that global optimization problem to global optimality as long as you find
Yeah, we
points.
find this. Yeah.
You keep on adding them. You can do tricks of that sort. But we find that we don't have to add too many points.
I guess as you're going through your global optimization, you know all the points.
You are
Where
collecting
is
lots of
negative?
points from global optimization. You are collecting lots of points from the simulator when you adaptive sample. When you sample adaptively, so you have lots of information.
I guess you can stop with the very first point where it's negative, right?
Of course. Yeah. And as I said, this is not a hard problem. The mixing is a nonlinear quadratic problems, Bayesian information criterion optimization. Those are the harder problems in the context of the methodology I'm describing. Some more types of constraint regression we can do. We can impose any kind of discrete condition on the model that you would like. So again, by way of an example, let's say these are my input variables, x1 through x4, and I'm postulating perhaps using quadratics as well as cubics and some logarithms. And let's say that I understand that these are the main effects and all those are secondary, and I don't want my secondary terms to show up in the model unless the primary effects are included. You can do that very easily with integer kinds of variables. We are solving integer programs anyway, so you might as well take advantage of that. So we have infrastructure here for imposing a constraint that says, unless you include this variable, don't include any of this in the model. You can go, you can do similar stuff. So if you're modeling genes, I guess, and you know that exactly one of these is going to be responsible for the quantity you are trying to model, you can put that constraint in there that says, give me no more than one of these variables in the final model. So we can have all these, group constraints enforced in the model. What we refer to as a group here is a collection of basis functions or basis functions and groups. And we can have requirements such as no more than a certain number of components of the group should be in the model. So we're trying to impose constraints that would give models that are sparser than normal. Okay? What I'm saying is these things can be done rather easily in the context of what we're talking about, and in fact, we have implemented them. They are available in the software. Okay, so I'm going to switch now, and for the remainder of my talk, I'm going to talk about how can I use this thing and what kinds of things can I do. Well, the first thing you're going to need is to actually download it, and it is available from MINLP.com, where we provide zip archives. Don't click at the software and expect it to install. You have to take the zip archive, unzip it, and put it somewhere in your path. And you can get licenses from that website as well, as long as you're an academic or a member of our consortium. You can get those online, and then you use it. Okay, how do you use it? Well,
what is CAPD?
It's the Center for Advanced Process Decision Making. We have a group of about 25 companies sponsoring our research. So the simplest thing you can do with Alamo is use it on a pre-existing data set. The data somewhere, you wonder whether the model you came up 20, 30 years ago is best. Well, you can try it with Alamo, see if indeed it was the best. So what Alamo will require is an input file, a text file, and it will give you back a text file with the results. So in this particular case, I'm showing an example with one input, one output in the model. I'm specifying the domain of my input variable, say between -5 and 5, and then I'm giving Alamo a number of data points, 11 in this case. Those of you who are quick with numbers, you can probably tell this is my x, my input, this is my z, the output. It's the square, of course. Well, in general, I don't know that this function is the square of that quantity over there. So I'm going to postulate a number of different functions. I'm going to tell Alamo, hey, use logarithms, use exponentials, consider sines, cosines, and some powers. 1, 2, 3, whatever. And if you look at all this, you have a total of 128 alternative models. You can do 128 alternative models in Excel, right? You can solve the problem I'm trying to solve here in Excel. Just take the data, put it into Excel, and compute for each different alternative the Bayesian information criterion, or the Akaike information criterion, or any other criterion you want. Or you can send this into Alamo, and Alamo is not going to enumerate all these alternatives. In fact, it's going to do an implicit enumeration because it's going to do branch and bound. It will enumerate a smaller number of these and eventually come back with the optimal solution, and will tell you, this is the best model, the square. Why? Because my Bayesian information criterion became -infinity. That's the best you can do. And all kinds of other metrics, R squares, and so on and so forth, are satisfied. They all look very good in this case. Okay? So even though you start with postulating a large number of functions, basis functions, Alamo came up with a very simple model. This is not a coincidence. That's what it's designed to do. And that's, in fact, what it does in practice. And here I have a comparison with other modeling approaches on a collection of 45 simple problems. These were problems with 1, 2, or 3 variables for which we postulated the problems as black boxes to these modeling techniques. And all these modeling techniques had access to the true basis functions, the basis functions that were actually in these models. And as you can see, if you run ordinary regression, you get models that the size of which tends to be very, very large. Sometimes if you do regression, you get coefficients of the form 10 to the 25th, and some other constraints with some other terms with coefficients, again, 10 to the 25th, but with a negative sign trying to cancel each other in certain parts of the domain. If you use lasso, you get much sparser models, as you can see, in comparison to regression. And of course, that's been known for a little while, but the assumption has been that the lasso gives you models that are as sparse as you would like them to be. The answer, well, what we are seeing here is that's not the case quite. Okay, Alamo, so basically, best subset selection, even for simple learning problems, will give you much simpler models than what you get with lasso. So you see here the median is right around 0. So basically, the number of terms in the surrogate model is very close to the number of terms in the true function.
It's because you have simplicity in your object function.
That's the objective. Yes, exactly. The objective is to go for the simplest possible model we can find. And the question was, is this sparse model sparse enough? And what we're seeing here is
Yeah, the objective function there is different.
Yeah.
And you're evaluating using...
we can argue, well, the L1 objective here is postulated as a proxy for the for sparsity.
But it's not a pick, though.
But it's not good enough. That's what I'm saying. It's not going to get all the way there. Another interesting thing
but
here.
yours is on the other side, though. I would rather have a little more complicated model than too simplistic and not
That depends.
It's like a false alarm versus misdetection.
That depends. That depends on how much you trust the information criteria and other kinds of things.
If you change the weight for the simplicity, would you move a little bit toward the right?
Like
which
of the criteria gave you?
You cannot go to the left from here. This is the absolute minimum you can get.
Yeah.
Right. And the other interesting thing here I wanted to point out is that the distribution in the case of ALAMO is negatively skewed, meaning ALAMO does simplify models. Give it a model and it has the ability to simplify things. Moving on now to the case of using ALAMO with a simulator. That's a bit more complex. I might have some pre-existing data set, I may not. But I want to complement it with more simulations, more measurements. I'm going to illustrate this in the context of a simple problem. I want to design a reactor. There's two variables here, basically. The length of the reactor and how much energy I put in there in terms of cooling water. So the idea here, I'm getting this CO2-rich gas coming, say, from a power plant. Too much CO2 in there. We want to extract CO2 by using this solid sorbent. And I have to remove heat from that reaction to happen, okay? So my goal here is to maximize the amount of CO2 I remove and to minimize the cost of cooling water into the system. Now there's only two variables here, as I said, the length of the bed that I denote here by L and the cooling water flow rate that I denote here by F. My primary objective is the removal of CO2, and basically I'm looking to figure out this function, removal in terms of length and flow rate. I postulated bounds here, make my problem well posed. As you can see, this is a large reactor, and in fact, people are interested in designing so large reactors at this point. So I postulated a bunch of basis functions, and as you can see, the model is very ugly, okay? Because I postulated a large number of functions, some linear, some quadratic, some exponential, some logarithmic, all kinds of little powers here and there, ratios, products, and so forth. And surely in the context of a single model, this is not too bad, but if you start thinking now in terms of a system composed of many pieces of this sort, things would be very complex if we were to use models as complex as this. So I would like to somehow simplify this model, and what ALAMO is going to do, it will start by taking perhaps a pre-existing data set, these points pre-existing. So ALAMO will start with those, it will compute the function values there. Well, actually, it takes those as input, but it will fit a model initially based on the initial data set. And then it will do more samples. Initially, of course, it will do those randomly, but then it will start using the adaptive sampling technique more and more. This snot fit tool. And as it takes more measurements, it will optimize. In this case, you are optimizing the Akaike information criterion. And I'm showing here at this stage with 4 measurements, the optimal AIC is to involve only 2 terms out of all those 60-some terms in the surrogate models. This is optimal because going with 1 term or with 3 terms increases AIC.
And so basically you had a 2 power 66 possible things, is that
correct? To do the 66, yes.
Okay.
A question, if you don't have simulation data, but you have the equations, complicated equations, can you simplify it? Or you have to go through generating the data?
You have to generate the points, yes. Yeah. We work with data, we don't work with the algebraic, with the explicit representation of the equations. So, and it will continue to take more points until eventually the sample error, the estimates are low enough to say my mean error is small enough, I'm going to terminate at this point. Okay? In this particular example, it terminated with 3 terms in the model. All right, so here's now what we can do with the model. Once I have the model, I can do all sorts of interesting things. It's an algebraic model, I can minimize, I can maximize. And of course, if I want to minimize cost of electricity, basically it says don't remove CO2 or remove as little as possible. If I want to maximize CO2, of course, it's going to say, well, you have to pay a lot in terms of electricity, in terms of cooling water. And if we could have it both ways, you would be at the point of utopia, but you cannot do this. So what you can do, in fact, you can generate the Pareto optimal curve. I have the model, and therefore I can generate this curve, and then I can decide where I want to sit on this curve, what level would make me comfortable in terms of expenses and CO2 removal. And then just closing the loop here, the dots here are from actual simulation. The black line that I had in the previous model, in the previous graph, so here this is the surrogate model, and the dots are from simulation, meaning my surrogate model is right on the money, it's perfect, provides a perfect representation of this particular system.
For this particular problem, once you get a model, it's actually a continuous model. There's no discretity variance, right? Once you get a model for this particular problem, it's a continuous variable model.
Yes, it's a continuous model.
You
yes.
don't have discrete variables.
That is quite correct. Yes. Yeah. Okay. Just a quick comparison between this sampling approach and other kinds of things that you might do. I'm comparing against those 45 functions that I talked about earlier. 3 modelers, ALAMO, the lasso, and ordinary regression, in which case I utilize the error maximization sampling that I described. So in the context of ALAMO, I can do any of these. Okay? And what I'm showing here in these performance profiles is the fraction of problems solved as I postulate here, as I specified a weaker tolerance. So for instance, this point here means that 70% of the problems were solved exactly by ALAMO. This point here means 80% of the problem had no more than 0.5% error with standard linear regression. All this is using ALAMO's adaptive sampling. If I now switch to using a simple Latin hypercube, all 3 modeling techniques, as you can see, take a hit. And in fact, in these 2 cases, you cannot even get to as high as you could get before. All we did here, basically, after solving the problems with error maximization, we knew how many data points ALAMO had sampled. And then we said, okay, let's do a single Latin hypercube with that number of data points. Okay, so there's nothing adaptive here, straight Latin hypercube. All I'm saying here is, because ALAMO has the ability to actually pick the location of those points, you can now extract more information than what you would extract out of the standard design of experiments kind of thing.
Do you have computational comparisons, like how long each one of them take?
This is going to take more time, but again, it's not a whole, it's not significant. We're assuming here that the simulator is much more expensive at the end of the day. But certainly here you don't do any computation. I mean, it's really straightforward to pick the point, whereas here you're doing some work. Yeah. But it's, as I said, it's small in comparison to the cost of simulation. Okay, now I'm going to go one step forward and do a more complex system. We've seen a small piece of equipment so far. Now let's think in terms of a system composed of many different pieces. Earlier, I had a single reactor. Now I have a bunch of reactors in series, and I have compressors around them. I have heat exchangers in these reactors, and so forth. I have to decide now here how many of these to use in series, how many to put in parallel. Other things I could think in terms of deciding here are optimal flow rates, the geometry of these reactors, sizes. Inside these reactors, remember the cooling water? Well, there's going to be heat exchanger tubes. The question is how many of those tubes to put in there. That will determine the heat removal rate. So we would like to optimize, assuming that we have detailed models for all these units. And the approach we're going to take is, again, we will build surrogate models for each of these units independently, and then we will put all those together into a single algebraic formulation to optimize. So here's the model now for the reactor, and it's now going to be more complex than what it was before, because I have about 16 inputs, 14 outputs in this particular system. And as you can see, I have quite a bit of detail in terms of mole fractions, geometry, heat exchangers, number of tubes. I can tell you even for the objective function here, for the cost of building these units, we have included the cost for taking the solid sorbent, lifting it with a lift, and dropping it on top of the reactor. Quite a bit of detail is what we had in the model, that there was no way to solve on top of a simulator, but now we will build the surrogate models, and here's an example of the surrogate model for this particular system. The pressure drop in the context of the reactor, as you can see here, is proportional to the length of the reactor with a few correction terms. That's the simplicity I was talking about earlier. I cannot look at a neural network and say, hey, it makes physical sense. But here, I can look at ALAMO's surrogate model and say, yes, I know pressure drop has got to be proportional to the length of the bed. Had this term not appeared there, I would have known there was something wrong in the data or the implementation.
How do you make sure those physical insights are kept in this model?
What we did, we tried to impose many non-negativity constraints for certain quantities we were modeling, like mole fractions and such. We tried to impose constraints on the sum of mole fractions equals to 1. So it was in part through the constraint regression feature of ALAMO.
You don't keep the structure like this or square function of this?
Yeah, and also maybe the basis functions also help, right? That could be based on the physical.
That can also be done, yes. We didn't do much in terms of trying to limit basis functions in this particular context. But the bottom line is, if you have a simple model, you can look at it and decide whether it makes sense physically or not. If it doesn't, then perhaps you need some more measurements or different basis functions to make progress. Okay, yeah.
The implication is that nature, at the end of the day, is as simple as a few linear models, and we're over a complicated life, or?
These are linear in terms of nonlinear transformations.
Yeah.
So they're not that linear at the end of the day. They are nonlinear, so as you can see here, I have a logarithm, I have some ratios, and so forth.
Yeah, but in any reaction, I would have the concentration times the exponent of the minus of the over temperature anyway, right?
Mm-hmm.
Linus expression, for instance. So,
Right, exactly. Yes.
How do you capture that and at the same time estimate the activation energy there?
Right. So you are doing some related work. We can talk about that later, but it gets a bit more complex. The principle is still the same. Information criteria based like
a nonlinear regression, I guess.
But you end up with nonlinearities in the regression, exactly. The integer variables are still there. Yeah. It's a much harder problem than what I'm talking about. At this point, ALAMO won't do it in purpose because that problem is much harder. At the current state, we are constraining attention to this kind of approach, linear in terms of simple nonlinear transformations. So you don't look at nested nonlinearity in the regression functions.
ALAMO 2.
Correct. All right, so now once I have the algebraic model, I can go and optimize it. This was a mixed integer nonlinear programming model with about 1,000 constraints and variables, a couple of hundred binary variables, and of course we can solve that with Baron again. And we'll come back saying use 3 of these exchanges in series, 2 on the other side, and it would optimize the geometry and everything in this particular system. Okay? All right, so in conclusion, we have a technology here where the aim is primarily to come up with models that are simple as possible, and we ask the question of what are the simplest kinds of models we can come up with in modeling from data, okay? And are those worth, spending CPU cycles for? We do have constraint regression capability that's unique in terms of what is out there in the literature, in the sense that we can impose constraints on the response surfaces themselves. The first 2 of these items are available in the implementation right now, so bounds on response variables and group constraints are there. We will put in constraints on gradients because they are important in many applications. And we know it's a simple thing to do. We understand how to do this. I should point out that this is not something we could have done 5 years ago. Why? Because bound was not there in terms of capability 5 years ago. Global optimization was not there 5 years ago. And also the derivative-free solvers were not quite there, up until very recently. Or at least we didn't know how to use them. At this point, the code is available. I invite you to use it and let us know how it works. And again, thank you for the invitation, and I'll be more than happy to take more questions.